in this section, we're gonna talk about new type of a function, kind of new, um, called power function. And power function is a function with a single term that is the product of a real number and a coefficient, and a variable raised to a fixed real number. So some examples of power functions is our area of a circle, pi r squared. So it's a single term function, and it has a coefficient of pi, and r, a variable, raised to power 2. Another example is the volume of a sphere function. Again, we have 4/3 pi r cubed, and again, it's a single term, and the coefficient is 4/3 pi. Don't forget that pi is a number. It's a infinitesimal, it's a rational number, but it is a number. So this whole thing, this is a coefficient, and the power of our variable r is 3. Okay, so here's a formal definition. Same as we said, it's a single term function with a coefficient and multiplied by the variable to power p, and both coefficient and p should be real numbers. Now, the question that I want you to ask is 2 to the x a power function? And I want you to think about it and answer. And if you need more time, please pause. So the answer is no, it's not a power function. It does not fit this definition because a 2 is not a coefficient here, it's a base. For the power function, power is a fixed number. It's a real number. It could be 2, 3, 4, 5. It could be a fraction, could be 1/2, it could be 3/7. It could be a negative number, -2, -3, -7/5. But even a radical, but it's not a variable. The point is it's a constant. And here for this one, x, the power is variable. It's x, and it's a different types of a function. It's an exponential function. We'll be talking about those later on, so don't confuse those two. Now, the next question is which functions of our power functions from this list? Again, I want you to pause here and think about it. And the answer is all of them. Okay, all of them are power functions. How so? Because we can rewrite our 1 as x to power 0. So remember, it's coefficient k, it could be 1, times x to some power. So this is 1 times x to power 0. This is just 1 times x to power 1. And then, okay, power 2, power 3. Now, what about 1 over x? Well, 1 over x is x to -1. And 1 over x squared is x to -2. So all of them are power functions. Now, what about square roots? Well, remember, we can write a root as a fraction as well. It's 1/2, right? So square root of x is x to the power 1/2. So whatever the index here, and when we have a square root, the index on the root is 2 by default. We don't write it, just like we don't write the coefficient of 1 here. It's there by default. We know it's there, but we don't have to write it. Same with the square roots. The index 2 is there, but we don't have to write it. So the index on the root goes into the denominator of your exponent, right? And the exponent is going to be rational or a fraction. Okay, and so similar, how would you rewrite cube root of x? It's x to power 1/3. So all of these are power functions, and we did a little review on rational exponents as well. So now I want you to think about this one. And I'm not going to give you the answer for it, and I want you to think about it and let me know what you think. So pause here if you have to, and we're going to continue. So if you did the activity on Desmos for to introduce power functions, you will notice that these functions that you see here, they're all even powered functions. So these are even powered functions, meaning your exponent is an even number, and all of them look similar to our x squared. So all of them have this U shape, right? And if the power, so first we start for x squared, it's our regular parabola, but as the power increase, what happens that here, these are very interesting points. All of them go through these points, -1, 1, and 1, 1. Okay, and after, like, outside of these points, so when x goes to the left, to the negative infinity, first of all, we want to notice that y also goes to infinity, right? And that's in words. And what we're going to do, we're going to use this notation as x goes to negative infinity, y, or we'll say approaches negative infinity, y approaches positive infinity. It grows without bound. Okay, so when y approaches infinity, we say it grows without bound. So for x, also x becomes very large, but on the left side, on the negative side. So this is called the end behavior of a function. So this is the end behavior on the left side. What about the end behavior on the right side? So as x approaches positive infinity, y, what happens to y? It goes up. It grows without bound again. So it approaches positive infinity. So see, these are similar, except so the same behavior if as x goes to the left or to the right, y goes up. So we could kind of consolidate both of these statements into one statement. We're gonna say as x approaches positive or negative infinity, y grows without bound and approaches positive infinity. So this statement, like I said, it combines both of those statements into one. Okay, so what else about the shape of these graphs? Well, we observe that as the exponent becomes larger, our graphs grow faster and faster and faster. So the slope of the tangent line will become steeper and steeper and steeper. If we wanted to do like to trace, kind of like check the slope with a ruler. So do you see how it becomes like steeper, more vertical? But On this interval, around 0, between -1 and the +1, it's the opposite. Like around 0, it follows closer to the x-axis for some time, and then they start growing faster. So up to a certain point, they grow slower than the x squared, and then they start growing faster. Okay, so what about these types of functions? How are they different? So the graph is different, right? So how are they different from the ones that we just talked about? And these are actually odd-powered functions. Meaning their exponent is an odd number, so like 5, 3, 7, and this is the pattern that they have. Okay, so what is the pattern? The pattern is when x approaches negative infinity, y actually goes down. The absolute value grows without bound, but towards mm, bottom, the negative side, towards the negative side. Yeah, so it's negative infinity. And when x approaches positive infinity on the right side, y also approaches positive infinity. So you see that the shape of the graph for these functions is different. It's very different from the one that we just saw. So you could actually figure out whether your power of the function is positive or negative based on the shape of their graphs. Okay, so and that's the and behavior, and we're not going to combine it into one statement because they're very different on both ends of the number line. So we want to specify that when x goes to negative infinity, then y goes to negative infinity. We don't want to guess if we combine like plus or minus together, it's not going to be clear when it goes to negative, when it goes to positive. Okay, so we're going to keep it like that, not combining. What else can we say about these functions? Well, what happens when we multiply, let's say, x to the third by a -1? What's going to happen? Let's say we have y, or f of x, equals negative x cubed. What's going to happen to this function? Well, what's going to happen, it's going to be reflected about the x-axis, right? That's the proper way to say it, and that's what they say in the books, but in common language, it's gonna flip, right? It's gonna flip upside down. So it's going to rotate about the x-axis. So, and again, these points, 1, 1 and -1, 1, they're kind of special. All those graphs go through those points. So my x cube that will be flipped, it's also going to go through those points. And also for the x cubed, kind of see, I want to make it kind of accurate. So this is what it's gonna look like. So for this function, what is the end behavior? As x approaches negative infinity, your y approaches positive infinity. And so it's going to be reversed, right? As x approaches positive infinity, y will approach a negative infinity. All right, so this slide, it summarizes the behavior, and the same thing is going to happen to the even power functions. When they multiply by a negative coefficient, they will rotate about the x-axis and open downwards instead of opening upwards. right? So this is what happens for k greater than 0 or positive k. These are our general shape for even and odd functions and their end behaviors that we just discussed. But when k value is negative, coefficient value is negative, those graphs rotate about the x-axis and the end behavior changes as well. Now, let's continue. So let's take a look at this function. We have f of x equals x to the 8 and says describe the end behavior. Well, it's an even power function, positive coefficient, +1. So this is what the graph is going to look like. It's basically your U shape. Oh, oops. Okay, so it's going to be as x approaches positive or negative infinity, y always goes to positive infinity. So this would be the end behavior of that graph. Now, the next one is identify the end behavior of negative x to the 9th. So this one is in odd power function. So it's gonna look like this, and it's not my graph yet. I'm not making it a solid line. It's just like, this is the general form of the odd powered function, and it should be symmetrical. Mine is not, but I mean, you got the point. But since our coefficient is negative right here, we have a -1 in front of it. That means it's going to be flipped over to rotated about the x-axis, and this is what it's going to look like. And okay, so we're going to say that as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches negative infinity. So that's the end behavior of this graph. Now I want you to try this problem. Describe the end behavior of the function f of x equals -5 x to the 4th. Again, pause here, and I'll see you in the next video where we're going to discuss polynomial functions.